Hi, my name is Eric Learning Miller, and I want to talk to you today about something I call learning from experience. This is work with many other people. Many of whom are in my lab, and this is a list of the contributors. I won't go through them all. The green ones are UMass folks, including faculty and students, and the others are collaborators from other institutions. So one of my primary motivations for figuring out what problems to work on in artificial intelligence and in computer vision is asking the following questions. What can humans do better than computers? And as computers get better and better and better, and keep adding skills to their list, we can slightly modify the question and say, what can humans still do better than computers? And I think even though computers are getting very impressive at many tasks, there's still a very long list of things we can answer this question. So one interesting exercise is to sort of think about a brief history of artificial intelligence through the lens of this question. So early in AI, a lot of people focused on the idea that humans can reason logically. And so this led to the development of rule-based systems, logic systems, and strong game-playing systems. After a while, we got tired of programming computers to do the things we wanted, and we noticed that humans can learn from examples, particularly from labeled examples of pictures and things like that. And this led to the development of supervised learning, where we can give the computer, say, 100 pictures of an apple and 100 pictures of a banana, and have it try to learn the difference between these two things. After having done this for a number of years, I was struck in 2000 when I was a graduate student by the fact that humans can learn from very few examples, even just one example sometimes. And I made my thesis about learning from one examples. This is developed into the sub area of what's called low shot learning. And even more recently, we've been focused on the fact that humans can benefit strongly from exposure to unlabeled data before being exposed to labeled data. So imagine you wanted to learn Spanish, but your class wasn't going to start for 6 weeks. So you decide to listen to the Spanish radio or Mexican radio for 6 weeks, even though you don't understand exactly what they're being said. It turns out this is a big help in preparing you to take a Spanish class. And we're trying to leverage these kinds of ideas in the development of unsupervised and self-supervised learning. So to try to give you a sense of what I'm trying to achieve in the next few years in my lab, let me tell you a little story about the apple farm, a little girl and a robot. So once upon a time, an intelligent robot and a little girl went to work on an apple farm. Neither one of them knew much about apples at the time. The little girl knew that apples were unusually red, or usually red and round, and she liked the taste of them most of the time. The robot knew how to tell the difference between an apple, a banana, a rhinoceros, and a speedboat because it had been trained on ImageNet, a standard computer vision data set. After 10 years of working on the farm, the little girl's father came to pay her a visit. On the same day, the robot's designer came to see how the robot was doing. The girl's father picked an apple from a tree and said, "What can you tell me about it?" The little girl, who was not so little anymore, smiled and said, "That's a new variety of macoon, but you picked it too soon. It wasn't ripe yet. As you can tell by the fact that the stem came with it, and when you picked it, and that there's a little bit of green near the center on the bottom." She went on for 5 minutes talking about that apple. The robot designer wanted to see how his robot would do. He held the apple in his hand and asked the robot, "What can you tell me about it?" The robot replied, "It's an apple." Now, so what has the robot failed to do here? The robot, despite working on an apple farm for 10 years, has failed to learn from its experience. If it wasn't explicitly instructed to learn something, then it didn't learn it. And however, when humans experience prolonged exposure to an environment, they naturally develop expertise, and robots don't. So this is one of the things I'd like to change. And to do that, we have to understand how humans do it and how we can replicate this capability in robots. So I'm going to talk briefly about 3 ways that we've investigated doing this to learn from experience without really being taught explicitly. Okay, let's go on to number 1, which is learning distance, a concept of distance from motion. So we would like our robots and our intelligent agents to be able to answer questions like, how far away do you think an apple is if it looks like this? And how about an apple tree like this? How far away do you think it might be? And of course, we could provide answers to this question, maybe 1 meter away for the apple and maybe 10 meters for the tree. Now, the question is, or estimating distance from images is a critical human skill, but one which we were never taught. So how did we learn it? And how can robots learn it? Well, a traditional approach might be to teach a robot about distance by learning from labeled examples. And what I mean by that is we give it pictures and a distance associated with those pictures, and we give it millions and millions of these pictures. But this is incredibly tedious because there's so many different objects and so many distances they could be at. So we're going to take a different approach in this work, which is to learn to associate motion and distance. And we published this work in ECCV 2018. So let me tell you a little bit about that. So I'm going to start this with a simple video of looking out the window of a train. Now, as you look at this video, you notice that something you already know, of course, that things that are closer to the train go by more quickly, and things that are far away do not appear to be moving much. And of course, you understand this is because of the perspective and the way images fall on your retina. But nevertheless, this is a very simple stimulus, and we want to mine that stimulus to see what we can learn from it, okay? So notice that if we see something that we might recognize, like a tree, this particular tree might clear in the video. And this tree down here, on the other hand, went by slowly. That is a very simple observation that a computer can make once it's learned how to recognize objects and to track them to estimate their speed. So in this work, we trained a neural network to learn how fast something will move in a video based on what it looks like. So in other words, we can have it try to learn to predict how fast something will go by in the video. And when I show you a big tree like this and say, how fast do you think it's going to go by? You would naturally say quickly, because you can tell it's close. That means you've learned a concept of distance and how it relates to the speed at which something goes by. So it turns out that when you train a neural network to predict how quickly something goes by, it naturally separates things into categories based on how far away they are. So that's one example of being able to learn from experience. It's a rich representation that turns out to be an incredibly important part of common sense. So a second project is learning to recognize your own mistakes. So we're going to start with a face detector that's been trained with lots of examples in a traditional way. I'm showing you an example here on the right of an image in which 3 faces have been detected and outlined with these green boxes. But we'd like to make it even better without collecting even more data. And I'm going to show you in a minute that this face detector was making some mistakes. This is work we also published at ECCV 2018. So let's take a look at this video. Now, here we see the output of a face detector, and now here it's going to make a mistake. It thought for a moment that this hand happened to look like a face, and it put a box around it. Now let's watch it make another mistake. It's doing lots of things correctly, but all of a sudden it's going to, for a second, put a red box on the back of his neck, which is of course not a face. And we'll look at one more example here, where it's again going to look at his hand as a face. Now, you'll notice that when the video does this, when the detector does this, it tends to consistently recognize the faces, but only rarely put a bounding box around something that's not a face. And we call this appearance of a single detection in a sequence of frames a flicker. So the detector kind of flickers on and flickers off. And we've noticed watching these that an isolated detection on one of these flickers in a sequence of video frames is likely to be a false positive, meaning it's probably wrong. So even though the detector doesn't inherently know the difference between these correct faces and this non-face here, which is accidentally identified as a face, we can use the fact that it's sporadic to guess that it's likely to be an error. Similarly, occasionally we'll be recognizing faces in each frame, and there'll be one face that's dropped out that the detector misses. So if we see a sequence of repeated detections with one missing in the middle, we can guess this we call an off flicker, and this is typically a false negative, which means there should have been a detection here. So we can run our detector on thousands of videos without any effort, just by scraping them off the web and running them, and collect these sporadic missing detections and isolated detections, these flickers, and set them aside as examples to retrain our detector. Okay, so just to reiterate, the idea is run the base detector on lots of videos, collect the flickers and label them automatically, and then retrain the detector using the automatically obtained data. This results in substantial improvements in the original detector, and the key point here is that this can simply run on its own and doesn't require any labeling from us. All right. So the third project I want to tell you about is something we've just started, and it's about learning how to represent concepts in a brain-like structure. Often these are called embeddings. And these representations or embeddings should have certain properties. In particular, we want to think about what properties should visual representations have. Well, it seems reasonable that if I see two different pictures of the same thing and I want to come up with a representation for it, that those two pictures of the same thing, two different pictures of the same thing, should have very similar representations since they represent the same thing. But pictures of two different things should have more different representations. This seems so obvious that it's hardly worth saying. But how do we achieve that? Well, if I give you two pictures, so I have two pictures of this car taken at slightly different times, and you can see that they're from slightly different angles, so they look a bit different. What I'm saying is, whatever the representation of this car is, I'd like the representation of this to be very, very similar since it's the same car. On the other hand, here are pictures of two different cars. One is the same car as above, and the other one is obviously a different car. And I'd like these representations to be a bit different. So how can I achieve this? Well, a traditional labor-intensive approach would be to collect lots of image pairs that were either same, meaning I have two images of the same object, or different, meaning I have two images of different objects, and train a neural network to make the representations of the same pairs similar while making overall the representations diverse. But here's an automatic way of doing this that's not labor intensive. We can simply get random videos and track random objects in the video and grab different shots of the same object from the tracks of the object. These are guaranteed to be the same object if our tracker works correctly. Then we take pairs of patches or pairs of images from the same object and use those to, we train a neural network to make the representations of those same pairs similar again. So this is a way of doing the same kind of thing, but in a fully automatic way. So so I'm going to show you a very short video here where notice there's a little box on the car here tracking a particular patch. And if I move forward a little bit, I can collect many different views of this car as it moves along and as its appearance is changing fairly substantially as it moves away from us. And I want to train a neural network to continue to make embeddings of these grabbed objects similar because they're the same object, and it should be relatively insensitive to the different views of that object. Okay, so I've talked about 3 different ways that humans can learn and develop concepts just by watching the world go by, even without teachers. And I'm calling this learning from experience rather than learning from data that's been arduously labeled by a researcher. And I think that as we develop these concepts, we'll be able to train algorithms to have rich new capabilities without having to prepare all the data for them in a very careful way. All right, thank you very much.